Imagine, if you will, that we're just floating out here, not a care in the world, surrounded by an endless, inky blackness that isn't really black at all, but teeming with invisible things. It's a bit like being in a super vast, super quiet ocean, but instead of water, we're drifting through what feels like nothing at all. Yet, this nothing is absolutely bursting with the stuff stars are made of. Think of it, a huge, swirling cloud, bigger than you could ever imagine. We're talking about a molecular cloud, a cosmic nursery where baby stars are just waiting to be born. It's not empty, it's full of gas and dust, microscopic bits of matter, floating around, bumping into each other gently, slowly. Now, it's easy to think of space as cold and unchanging, but it's actually a bustling, dynamic place. These clouds, they aren't perfectly uniform. There are always little bumps and wiggles, denser spots here, thinner spots there. It's like a giant, cosmic dust bunny, but one that's so vast it makes our entire solar system look like a tiny speck. Over incredibly long stretches of time, these tiny differences start to matter. Imagine a whisper, so faint you almost don't hear it. But if enough whispers gather together, they become a murmur, then a hum, and eventually, a roaring sound. That's a bit like what happens here. Gravity, that invisible pull that keeps your feet on the ground and the planets orbiting the sun, is the true architect of stars. In these vast molecular clouds, gravity starts to work its magic on those slightly denser spots. It's a very subtle pull at first, almost imperceptible. But every tiny bit of gas and dust has a little gravitational tug on every other bit. So, those slightly denser regions, they start to pull in more gas and dust from their surroundings. It's a slow, gentle process, like a snowball rolling down a very, very long and gentle slope, gathering more snow as it goes. If you like listening to quiet stories about space and stars, please tap the like button. It helps others find this peaceful place too. And if you want to come back for more calm journeys through the universe, please like and subscribe. Enjoy what I do here, and let me know in the comments where you're tuning in from and what time it is for you. It's always fascinating to see who's joining us from around the world. Now back to the story. As these regions collect more material, they become even denser, and their gravitational pull gets a little stronger. It's a wonderful kind of cosmic feedback loop. More stuff means more gravity, and more gravity means more stuff gets pulled in. This process continues for millions of years. Can you picture it? You're floating there, just watching as wisps of gas slowly, almost imperceptibly, drift towards a central point. It's not a rapid collapse, it's more like a slow, majestic gathering. These collapsing regions are what we call stars. They aren't stars yet, not in the way we usually think of them. They're more like star babies, still in the womb of the cosmic cloud, getting ready for their grand entrance. They're gathering their strength, pulling in more and more material, growing bigger and hotter in their cores. At this stage, the protostar is still cloaked in a veil of gas and dust, so we can't actually see it with our eyes in the visible light spectrum. It's like a secret, hidden away. But if you could feel the universe, you'd start to feel a subtle warmth emanating from these dense cores. They're glowing, but mostly in infrared light, a type of light our eyes can't see, but our instruments can. It's like a soft, hidden ember, slowly getting brighter, promising something magnificent to come. The pressure and temperature in the very center of these collapsing clouds are rising steadily as more and more material piles on. It's a long, slow squeeze, building up to something truly explosive. So, we're still patiently observing our protostar, this magnificent cosmic embryo, hidden within its cocoon of gas and dust. It's getting bigger, remember? More and more material is falling onto it, and as it does, a truly fascinating thing happens. The material doesn't just fall straight down. Imagine water going down a drain. It swirls, right? The same principle applies here, but on a grander, much slower scale. As the gas and dust fall towards the center of the protostar, they start to flatten out into a spinning disk. We call this an accretion disk, and it's a swirling masterpiece of cosmic material. Now, why a disk? Think about a figure skater pulling their arms in as they spin. They spin faster. It's a bit like that with the cloud. As it collapses, any tiny bit of initial rotation gets amplified, and to conserve this spin, the cloud flattens into a disk. So, You're watching this immense, swirling flat pancake of gas and dust, all slowly spiraling inwards towards the very heart of the protostar. This disk is incredibly important, not just for the star itself, but because it's where planets will eventually form. Yes, you heard that right. The very beginnings of worlds like our own Earth are swirling around these baby stars. It's like a cosmic construction site, with all the building materials laid out, waiting for assembly. As more and more material falls onto the protostar and collects in this disk, the core of the protostar gets hotter and hotter, and the pressure within it builds to unimaginable levels. Think about squeezing something incredibly tightly. The harder you squeeze, the hotter it gets, right? The same principle, but with the entire weight of unimaginable amounts of gas and dust pressing down. This intense heat and pressure are critical. They are the conditions needed to ignite the star. For millions of years, the protostar continues to gather mass, shrinking and heating up. It's a bit like a cosmic pressure cooker. The heat in the core rises to millions of degrees. And then, finally, after all this time, all this squeezing and gathering, something truly spectacular happens. The temperature and pressure at the very center of the protostar becomes so extreme that nuclear fusion begins. Now, nuclear fusion sounds like a very complicated science fiction term, but let's break it down simply. Imagine you have two tiny building blocks, like little hydrogen atoms, which are the most common elements in the universe. Under these incredible conditions in the protostar's core, these hydrogen atoms are moving so fast and are squeezed so tightly together that they actually fuse or stick together to form a slightly heavier element, like helium. When they do this, a tiny bit of their mass is converted into a huge burst of energy. It's like a cosmic sparkle, happening billions upon billions of times every single second in the star's core. This release of energy is what makes a star shine. It's the very definition of a star. When fusion ignites, the protostar has officially become a main sequence star. It has found its balance. The outward push from all that energy created by fusion perfectly balances the inward pull of gravity trying to collapse the star. It's a delicate dance, a cosmic tug-of-war, where neither side fully wins, and that balance is what keeps a star stable for billions of years. Our own sun is a main sequence star, right now, happily fusing hydrogen into helium in its core, bathing our world in warmth and light. So, for the first time, you could truly see it, shining brightly. The strong winds from the newly born star, called stellar winds, along with the intense radiation, start to blow away the remaining gas and dust from the surrounding accretion disk. It's like a grand cosmic unveiling. The star is finally revealed in all its glory, shining brightly, a beacon in the vast darkness, the very first breath, the very first light of a brand new star. It's truly a magnificent sight, a celestial newborn, ready for a long and luminous life. Can you feel that warmth spreading through the emptiness? That's the power of a star, freshly born. So, here it is, our star, newly ignited and shining brilliantly. This is the main sequence phase, and it's the longest part of a star's life, like a long, steady adulthood. For a star like our Sun, this stage lasts for billions of years. Imagine billions of years, just consistently shining, warming, and providing light. It's truly mind-boggling when you think about it. During this time, the star is in a perfect cosmic balance. The immense inward squeeze of gravity is perfectly counteracted by the outward push of energy from the nuclear fusion happening in its core. It's like a cosmic arm wrestling match where neither side ever really wins, and that stalemate is what makes the star so stable. Inside the star's core, hydrogen atoms are constantly being mashed together to form helium, releasing that incredible burst of energy we talked about. This energy then slowly, patiently, makes its way from the scorching hot core through the layers of the star and eventually escapes into space as light and heat. It's a bit like warmth radiating from a bonfire, but on a scale that defies imagination. You can almost feel the gentle hum of that constant, powerful process, a feeling of steady, reliable energy flowing outwards into the vastness. The size and color of a main sequence star depend on how much stuff, how much mass, it was born with. Bigger, more massive stars are hotter and shine blue or white. They're like the giant, super bright spotlights of the universe. Smaller stars, like our Sun, are yellow or orange, and are more like cozy, warm lanterns. And even smaller stars, called red dwarfs, are cool and dim, glowing a faint red, almost like a dying ember, but they can last for trillions of years. Can you picture all these different stars, scattered across the galaxy, each one a different shade and brightness, a cosmic rainbow? Our Sun, a lovely yellow main sequence star, has been burning steadily for about 4.5 billion years, and it's got about another 4.5 billion years to go in this phase. That's a lot of stable, reliable sunshine for Earth, isn't it? It's important to remember that all this energy, all this light and warmth, comes from that tiny process of hydrogen fusing into helium deep inside the core. It's the universe's most efficient power plant, running quietly and consistently for eons. But what happens when a star starts to run out of its main fuel, its hydrogen? Well, just like anything that uses up its fuel, a star can't keep going forever in the same way. This is where things get really interesting, and the star begins its next great transformation. The star has been a steady, predictable friend, but now it starts to prepare for a spectacular change. Imagine a grand old tree that has stood tall for centuries. It doesn't just disappear. It changes, sheds its leaves, and eventually, though still magnificent, takes on a different form. A star does something similar, but on an infinitely grander scale. As the hydrogen fuel in the core begins to dwindle, something crucial shifts. The core, no longer having as much outward pressure from fusion, starts to feel the relentless squeeze of gravity more strongly. It begins to contract, getting denser and hotter. This isn't fusion in the core anymore, this is just the core shrinking under its own weight. This contraction, strangely enough, makes the layers of hydrogen around the core get hot enough for fusion to begin in a shell surrounding the core. It's like the main engine is sputtering, but a smaller, secondary engine kicks in around it. This shell fusion produces a lot of energy, even more than the core fusion did when the star was on the main sequence. This extra energy pushes the outer layers of the star outwards, causing the star to expand dramatically. It swells up, becoming much, much larger than it ever was before. Its surface cools as it expands, which makes it glow red. This is why it's called a red giant. Our Sun, in about 5 billion years, will become a red giant. Imagine our cozy yellow Sun swelling up so much that it swallows Mercury, Venus, and possibly even Earth. It will be an absolutely immense, glowing red orb in the sky. Can you picture that incredible, fiery expansion? It's a truly majestic, if somewhat terrifying, thought. The star has left its comfortable adulthood and is now entering a grand, expansive old age. So, our star has expanded into a red giant, a truly immense, glowing orb. It's a bit like a grand, cosmic sigh, a stretching out after billions of years of steady work. This phase, while still long, is much shorter than the main sequence. For a star like our Sun, it might last only a few 100 million years. Inside, the core is still shrinking and getting hotter, even as the outer layers puff outwards. The hydrogen fusion is now happening in that shell around the core, furiously generating energy and pushing the star's atmosphere far, far out into space. If you were floating nearby, you'd feel an immense, radiating warmth, but the surface of this red giant would actually be cooler than it was when it was a main sequence star. It's like spreading a small amount of heat over a much, much larger area. Imagine taking a hot coal and expanding it to the size of a house. The overall house would be warm, but the surface wouldn't be as scorching as the tiny coal was. That's why it glows red. The sheer size, though, would be breathtaking. Picture our Sun, a cozy yellow sphere, now swollen to the point where it engulfs planets. It's an awe-inspiring, if slightly terrifying, transformation. Now, as the core of this red giant continues to shrink and heat up, something new starts to happen, especially for stars that are around the same size as our Sun. The temperature and pressure in the very center of the core eventually reach a critical point. They become hot enough and dense enough to begin fusing helium into heavier elements, like carbon and oxygen. This is a new type of fusion, a new power source for the aging star. It's like the star has discovered a deeper, more powerful reserve of fuel. When this helium fusion ignites, it can be quite a dramatic event for some stars, especially those around the Sun's mass, in what's called a helium flash. It's a rapid, uncontrolled ignition of helium in the core, a sudden burst of energy that quickly stabilizes. After this initial burst, the star finds a new kind of equilibrium. It settles down again, though it's still much larger and cooler than it was in its main sequence days. The star is now burning helium in its core and hydrogen in a shell around that core. It's like a dual-engine cosmic machine. For stars like our Sun, this new phase of helium burning doesn't last nearly as long as hydrogen burning did. Helium is a heavier fuel, and it burns much faster. Think of it like burning logs versus kindling. The logs burn hotter and quicker. As the helium in the core gets used up, the star starts to face another energy crisis. The core, now mostly carbon and oxygen, begins to contract again, and the outer layers expand once more. The star becomes even larger and cooler, sometimes called an asymptotic giant branch star, or AGB star for short. It's essentially a second red giant phase, even grander and puffier than the first. During this AGB phase, the outer layers of the star become very loosely held by gravity. They are so far away from the core, and the star is generating so much energy that these outer layers begin to gently drift away into space. It's not an explosion, not yet anyway. It's more like a slow, steady exhalation. The star starts to shed its outer skin, gently releasing vast amounts of gas and dust into the surrounding universe. Can you imagine the serene beauty of that? A star slowly, gently, letting go of its outer embrace, sending its building blocks out to mingle with the cosmic currents. These expelled layers of gas and dust form a beautiful, expanding shell around the dying star, creating what we call a planetary nebula. Now, don't let the name fool you. It has absolutely nothing to do with planets. The name comes from early astronomers who saw these objects through their telescopes and thought they looked a bit like planets. But in reality, they are stunning, colorful clouds of gas, lit up by the incredibly hot, exposed core of the dying star at their center. Each planetary nebula is unique, a cosmic artwork, displaying intricate patterns and vibrant colors like emerald greens, ruby reds, and sapphire blues. Imagine yourself floating just outside one of these, watching the delicate tendrils of gas swirl and glow, like cosmic smoke rings. Each one is a final, beautiful hurrah, a colorful farewell from a star that has lived a long and luminous life. So, we're mesmerized by the glowing spectacle of the planetary nebula, those incredible, colorful clouds of gas gently drifting away from our dying star. This is truly a cosmic masterpiece, a vibrant send-off. The star itself, having shed its outer layers, is now exposed as a tiny, incredibly hot, and super dense core. This is what's left behind after all those billions of years of shining and fusing. It's no longer fusing hydrogen or helium. The fusion reactions have completely stopped. This exposed core is called a white dwarf. Imagine taking something as big as our Sun, something that once swelled up to be even bigger than Earth's orbit, and squeezing almost all of its material into a sphere roughly the size of Earth. That's how incredibly dense a white dwarf is. A teaspoon of white dwarf material would weigh tons, perhaps even more than an elephant. Can you even begin to picture that kind of density? It's like the universe has compacted a giant into a tiny, incredibly heavy pearl. It's still incredibly hot when it first forms, glowing with a brilliant white light from its leftover heat, which is why it's called a white dwarf. The planetary nebula, that beautiful cloud of gas, continues to expand outwards, slowly fading and dispersing into the vastness of space over tens of thousands of years. Eventually, it will become so spread out that it simply blends back into the interstellar medium, the general gas and dust floating between the stars. It's like a beautiful puff of smoke dissolving into the air, its colors slowly dimming until it's invisible. But the white dwarf, that tiny, dense core, remains. This white dwarf is essentially a stellar cinder. It doesn't have any internal nuclear fusion going on anymore. It's just a remnant, slowly cooling down. Think of a dying ember from a campfire. It glows red for a while, then orange, then just a faint flicker, before finally turning cold and black. A white dwarf goes through a similar, but incredibly slow process. It radiates away its stored heat into space. This cooling process takes an extraordinarily long time, far longer than the current age of the universe. We're talking trillions of years. Over these immense timescales, the white dwarf will continue to cool, getting dimmer and dimmer. Its white glow will eventually fade to yellow, then orange, then red. Eventually, after unimaginable eons, it will become completely cold and dark, a black dwarf. This black dwarf would be an inert, solid lump of carbon and oxygen, drifting silently through the cosmic void, a testament to a star that once shone brightly. It would be incredibly difficult to detect, as it would emit no light or heat of its own. It's like a cosmic ghost, a memory of a star. However, it's important to note that no black dwarfs have ever been observed, simply because the universe isn't old enough for any white dwarfs to have cooled down completely. So, for now, they exist only in our theoretical understanding of how stars meet their ultimate, quiet end. This fate, this gentle fading into a white dwarf, and then eventually a black dwarf, is the destiny for stars like our Sun, and for all stars up to about 8 times the mass of the Sun. They live long, stable lives, have a magnificent final expansion as a red giant, shed their outer beauty as a planetary nebula, and then slowly cool down into stellar remnants. It's a peaceful, quiet ending, a slow descent into darkness after billions of years of shining. It's a beautiful thought, isn't it? The universe taking back the building blocks, releasing them to perhaps form new stars, new planets, new life, sometime far, far in the future. The cosmic cycle continues, even in death. Let's dive back into our cosmic narrative, moving from the quiet, graceful end of sun-like stars to the truly explosive finales of their massive counterparts. So, we've explored the serene, gentle fading of stars like our Sun into white dwarfs. But now, let's turn our attention to the true giants of the cosmos. Imagine stars that are 8 times, 10 times, even 100 times more massive than our Sun. These colossal stars live fast and die hard. Their lives are much shorter, often lasting only a few million years compared to the billions of years for a star like our Sun. It's like they're burning through their fuel at an incredibly furious pace, living life in the fast lane. Just like smaller stars, these massive stars spend most of their lives on the main sequence, fusing hydrogen into helium in their cores. But because they are so much more massive, their cores are much hotter and denser. This means fusion happens at a much, much higher rate. They are truly the brightest beacons in the night sky, often shining with a brilliant blue or white light. You can almost feel the intense energy pouring off them, a radiant heat that would simply vaporize anything that got too close. When these massive stars start to run out of hydrogen in their core, they also expand and become supergiants. Not just red giants, mind you, but supergiants. We're talking about stars so immense that if one replaced our Sun, its outer layers could extend past the orbit of Jupiter, or even Saturn. Imagine our entire solar system swallowed whole by a single colossal star. It's a breathtaking and humbling thought. These supergiants are often reddish, just like their smaller counterparts, but on a scale that is almost impossible to comprehend. Now, here's where the difference truly begins. For these massive stars, when the hydrogen in the core is used up, and even when helium starts fusing into carbon and oxygen, the story doesn't end there. Their immense gravity keeps squeezing the core, making it hotter and hotter, denser and denser. This intense pressure allows these stars to fuse heavier and heavier elements. They become like cosmic onion layers, with different fusion reactions happening in shells around the core. First, helium fuses into carbon and oxygen. Then, carbon fuses into neon and magnesium. Then neon into oxygen and silicon. And finally, silicon fuses into iron. This process continues, building up heavier elements in the core, layer by layer, until the very center is filled with iron. And this is where the star hits a wall. Iron is unique. When iron atoms are fused together, they don't release energy, they absorb it. It's like trying to build a fire with damp wood that just soaks up all the heat instead of giving it off. So, once the core of a massive star is filled with iron, there's no more energy being generated to push outwards and counteract the crushing force of gravity. At this point, the cosmic balancing act that kept the star stable for millions of years suddenly, catastrophically, fails. The core, no longer supported by outward pressure from fusion, collapses in on itself with incredible speed. We're talking about something the size of Earth, collapsing to the size of a city in mere milliseconds. This is an implosion of unimaginable power. As the core collapses, it bounces back, sending a powerful shockwave hurtling outwards through the star's layers. This rebound, this outward-moving shockwave, is what triggers one of the most spectacular events in the universe, a supernova. It's an explosion so powerful that for a brief period, a single supernova can outshine an entire galaxy. Imagine that. One star, for a few weeks, brighter than hundreds of billions of stars combined. It's an almost blinding flash, a cosmic exclamation point, marking the dramatic death of a massive star. If you were close enough, you wouldn't just see it, you'd feel it, a colossal wave of energy washing over you. This explosion blasts most of the star's material, including all those heavy elements created during its life, out into space at incredible speeds. These elements, like oxygen for our air, carbon for our bodies, and iron for our blood, were forged in the heart of these dying stars. We are, quite literally, made of stardust. Let's continue our journey, now witnessing the awe-inspiring, cataclysmic explosion of a supernova. So, the supernova has just erupted, a truly mind-boggling spectacle of light and energy. Imagine yourself floating at a safe distance, not too close, of course, but close enough to truly appreciate the scale. The star that was once a magnificent shining giant has, in a breathtaking instant, become an expanding bubble of incandescent gas, racing outwards at speeds that defy comprehension. This isn't just light, it's a colossal wave of matter, energy, and radiation, painting the cosmic canvas with ephemeral brilliance. For a short time, this one star's death throws outshine the collective glow of entire galaxies, a testament to the sheer violence of its end. The beauty of a supernova, beyond its blinding brilliance, lies in what it creates. This explosive event isn't just destruction, it's also the greatest act of cosmic creation. All those heavy elements, everything from the oxygen we breathe, the carbon that forms the basis of life, the iron in our blood, the silicon in our computers, and even heavier elements like gold and silver, were forged in the fiery heart of these massive stars, and then, in their dying moments, scattered across the universe by these colossal explosions. Without supernovae, there would be no planets, no us. We are, quite literally, children of the stars, made from the very dust they expelled in their magnificent deaths. You can almost feel the echoes of that creation, sensing the ancient atoms swirling around you, each one a tiny piece of a cosmic explosion. After the initial blinding flash subsides, the supernova remnant continues to expand. It forms a beautiful, intricate, and often turbulent cloud of gas and dust, glowing with the leftover energy from the explosion. These remnants can be seen for thousands of years, slowly dispersing into the interstellar medium, enriching it with the very elements needed for the next generation of stars and planets to form. It's a profound thought. The death of one star fuels the birth of others. The cycle of cosmic life and death is endlessly intertwined. But what's left behind at the very center of that furious explosion? The fate of the stellar core after a supernova depends entirely on how massive the original star was. Remember that incredibly dense iron core that collapsed? Well, if the original star was somewhere between about 8 and 25 times the mass of our Sun, the core, after collapsing and rebounding, doesn't entirely blow itself apart. Instead, it gets squeezed to an almost unbelievable degree, far beyond the density of a white dwarf. The gravity is so intense that electrons and protons are forced to combine, turning into neutrons. All the empty space within the atoms is crushed out of existence. What's left is a super-dense ball made almost entirely of neutrons, called a neutron star. Imagine a star with twice the mass of our Sun, but squeezed into a sphere only about 10 to 20 kilometers across, roughly the size of a small city like Randers. This is the most extreme density we can possibly imagine, short of a black hole. A teaspoon of neutron star material would weigh billions of tons. If you could somehow hold a piece of it, you would simply be crushed by its immense weight. The gravity on its surface would be so strong that if you dropped a feather, it would hit the surface with the force of a nuclear bomb. Neutron stars are often born spinning incredibly fast, sometimes hundreds of times a second, because all the spin of the original star is concentrated into this tiny, dense sphere. And many of them also have incredibly powerful magnetic fields. When a rapidly spinning neutron star with a strong magnetic field sends out beams of radio waves from its poles, like a cosmic lighthouse, We detect them as regular pulsars. These are called pulsars. Imagine a universe full of these cosmic lighthouses, spinning away, sending out their rhythmic, almost hypnotic beats across the vast emptiness. It's a very strange, very fascinating remnant of a star that lived and died in a blaze of glory. It's a truly alien world, ruled by the most extreme physics. So, you're floating there, trying to wrap your mind around a star that's been squashed down to the size of a city, spinning faster than a blender, and radiating invisible beams of energy. It's a truly mind-bending concept, a testament to the extreme forces at play in the universe. Imagine trying to stand on its surface. The gravity would be so immense, you'd be instantly flattened into a microscopic smear. It's a place where the laws of physics as we know them on Earth are stretched to their absolute limits. If a pulsar is nearby, you can almost hear the rhythmic ticking sound it would make if sound could travel in space, like an enormous ancient clock counting down cosmic eons. But even a neutron star isn't the ultimate end for all massive stars. What happens if the original star was even more massive? We're talking about stars that were truly gargantuan, perhaps more than 25 or 30 times the mass of our Sun. These are the absolute heaviest heavyweights of the cosmos, and their demise leads to something truly enigmatic and awe-inspiring: a black hole. For these supermassive stars, when their iron core collapses during the supernova, the implosion is so powerful, the squeeze so intense, that even the incredible forces that create a neutron star aren't enough to stop the collapse. The core continues to shrink, getting denser and denser, until all its mass is compressed into an infinitely small point, a singularity. This point has such an incredibly strong gravitational pull that nothing, not even light, can escape from it. This is a black hole. Now, it's important to understand that a black hole isn't actually a hole in the traditional sense, and it's not really black because it's a physical object. It's better to think of it as a region of space where gravity is so overwhelmingly strong that it warps space and time around it. The boundary around this region, the point of no return, is called the event horizon. Imagine trying to paddle a canoe upstream on a river. If the current is too strong, you eventually reach a point where you can paddle as hard as you like, but you'll never make any progress forward. The current just drags you back. The event horizon is like that point in the river for light and everything else. Once you cross it, there's no turning back. If you were to approach a black hole, you wouldn't necessarily notice anything unusual from far away. Its gravity would be just like any other object of the same mass. But as you got closer and closer to the event horizon, things would start to get really weird. Time would appear to slow down for you relative to someone far away, and the light from the universe behind you would seem to get stretched and distorted. If you were to cross the event horizon, from your perspective, you'd just keep falling inwards, but from the perspective of someone outside, you would seem to freeze at the edge, fading from view as your light could no longer escape. It's a truly mind-bending concept that pushes the limits of our understanding of physics. Black holes are often portrayed as cosmic vacuum cleaners, sucking everything up, but that's not quite right. They only suck if you get too close. If our Sun were to suddenly turn into a black hole of the same mass, Earth would simply continue orbiting it exactly as it does now. It would just get very, very cold and dark. However, if gas and dust or even other stars get too close to a black hole, they can be pulled into a swirling accretion disk around it, heating up to incredible temperatures and emitting powerful X-rays and gamma rays before finally crossing the event horizon. This is often how we detect black holes, not by seeing them directly, but by observing the intense energy emitted by the material spiraling into them. So, from the humble beginnings of a gas cloud, to the long, steady life as a shining star, through the dramatic expansion of a giant, the beautiful farewell of a nebula, and finally, for the most massive, the cataclysmic supernova and the mysterious birth of a black hole or neutron star. It's a grand, unending cycle of creation and destruction, energy and matter, constantly transforming in the cosmic dance, and every atom in your body has been part of this magnificent journey. We've seen the spectacular birth and diverse deaths of stars, from the quiet fade of a white dwarf to the immense power of a supernova, leading to a neutron star or black hole. But this isn't truly the end of the story. The universe is a grand recycler, and death in the cosmos is often just a prelude to new life. All that gas and dust, All those heavy elements blasted out by supernovae or gently shed by planetary nebulae, they don't just disappear into nothing. They drift through the vast, cold emptiness of interstellar space. Imagine yourself now, floating not near a star, but between them, in the truly immense stretches of the galaxy where stars are few and far between. It's mostly empty here, but not entirely so. There are incredibly thin wisps of hydrogen and helium, the original building blocks of the universe, along with the heavier elements that earlier generations of stars forged and then returned to the cosmic soup. This is the interstellar medium, a diffuse sea of gas and dust that permeates our galaxy. You might see faint, shimmering clouds, almost ghost-like, that are too spread out to shine brightly, but they are there, the raw material for everything to come. These clouds of gas and dust, though incredibly sparse, are the fertile ground for new stellar nurseries. Just like in the beginning of our story, tiny variations in density exist within this interstellar medium. Over immense stretches of time, gravity, that tireless sculptor, begins to work its magic again. It subtly pulls together these scattered atoms and dust grains. This is the beginning of a new molecular cloud, a fresh cosmic womb. It's a bit like dust bunnies, slowly gathering under your bed, but on a galactic scale, and instead of just collecting dust, they are gathering the very ingredients for stars, planets, and even life. The key difference for these new clouds is their composition. Unlike the very first stars that formed in the universe, which were made almost entirely of hydrogen and helium, these new clouds are enriched with all those heavier elements that came from the deaths of previous stars. Remember the carbon, oxygen, iron, and all those other elements created in stellar cores and supernovae? They're all mixed in now. This enrichment is absolutely vital. Without these heavier elements, rocky planets like Earth couldn't form, and without rocky planets, life as we know it might not exist. So, in a very real sense, the death of old stars provides the necessary ingredients for the birth of new, more complex systems. As these new molecular clouds grow denser, they eventually fragment and collapse under their own gravity, just like we discussed at the very beginning. Each collapsing fragment then becomes a new protostar, pulling in more material, getting hotter and denser in its core, until, eventually, nuclear fusion ignites. A brand new star is born, shining its first light into the cosmos, often surrounded by a swirling protoplanetary disk made of the leftover gas and dust. This disk, rich in those heavier elements, is where planets, moons, asteroids, and comets will eventually coalesce. It's truly a beautiful, continuous cycle. The universe doesn't throw anything away. It recycles its building blocks, creating new generations of stars, each one a little different, a little richer in ingredients than the last. Can you imagine witnessing this entire grand cycle, floating from the gentle gathering of dust, through the fiery birth and long life of a star, its majestic death, and then seeing its remnants become the very seeds of new beginnings? It's an unending cosmic ballet, a testament to the universe's incredible ability to renew itself. Every atom in your body, every breath you take, every solid object around you, has been part of this extraordinary journey, forged in the heart of stars and scattered by their magnificent ends. We are truly, profoundly connected to this vast recycling universe. So, we've witnessed the grand recycling act, where the ashes of old stars become the ingredients for new ones. It's a beautiful thought, isn't it? Every time you look up at the night sky, every twinkling point of light is a star, perhaps like our sun, quietly performing its life's work, or perhaps a massive blue giant, living its short, intense existence, or even a dying red giant, gently exhaling its final breath. Each one is a unique chapter in this cosmic story, and each one plays a role in the grand ballet of creation. Now, let's talk a little more about those heavier elements that get scattered. It's truly amazing to think about. When the very first stars formed after the Big Bang, they were simple. Just hydrogen and helium, the lightest elements. There was no carbon, no oxygen, no nitrogen, no iron, no building blocks for rocky planets, no ingredients for water, no components for life. These elements had to be made, and they were, in the incredible furnaces of stars. Think of a star as a cosmic chef, cooking up all the ingredients needed for everything around us. The carbon in your pencil, the oxygen in the air you breathe, The calcium in your bones, the iron in your blood, even the gold in a piece of jewelry. All of it was forged in the fiery heart of a star that lived and died long, long ago. Imagine reaching out and feeling the tiny dust motes around you in this interstellar space. Each one could be a microscopic shard of a star that exploded millions or billions of years ago, carrying the very atoms that will one day make up new worlds. It's a humbling thought, how connected we are to these distant, powerful cosmic events. Our very existence is tied to the death of stars. As new stars form from these enriched clouds, not all the gas and dust makes it into the star itself. We talked about the protoplanetary disk, that swirling flat pancake of leftover material surrounding a newborn star. This disk is where the true magic of planet formation happens. Within this disk, the dust grains, tiny bits of carbon, silicon, and iron, start to gently bump into each other. They stick together, slowly, gradually, building up into larger and larger clumps. It's like cosmic snowballs forming, but instead of snow, it's tiny bits of rock and metal. Over millions of years, these tiny clumps grow into bigger and bigger rocks, then into what we call planetesimals, which are like small, baby planets. These planetesimals continue to collide and merge, slowly clearing out their orbits around the young star. The inner parts of the disk, closer to the hot young star, are warmer, so only materials that can withstand high temperatures, like rock and metal, can condense there. This is why we get rocky planets like Earth and Mars in the inner solar system. Farther out, where it's much colder, ice can also form, allowing giant planets made of gas and ice, like Jupiter and Saturn, to grow much larger. Can you picture this grand construction project? A young star, newly ignited, surrounded by a dusty, swirling disk, and within that disk, bits of matter slowly, patiently coming together, building worlds. It's a quieter process than a supernova, a slow, meticulous assembly, but no less profound. And it all begins with the richness provided by the deaths of earlier stars. The elements created in stellar cores are not just scattered, they are gathered, sculpted by gravity, and assembled into new homes for future possibilities. So, the life cycle of a star isn't just about a single star's journey. It's a grand, interconnected cosmic dance. It's the story of how the universe builds itself, layer by layer, from the simplest beginnings to the rich complexity we see today. From hydrogen and helium to all the elements on the periodic table, forged in the hearts of stars and scattered by their magnificent ends, only to be recycled into new suns and new planets. And somewhere out there, on one of those newly formed planets, perhaps life might even begin, built from the very same cosmic dust. We've seen the universe as a magnificent, self-renewing system, constantly taking the remnants of the old to forge the new. It's a story whispered across billions of years, written in the light of distant galaxies, and in the atoms that make up everything around us. Think for a moment about the elements. We talk about hydrogen, helium, carbon, oxygen, iron. These aren't just abstract scientific terms, they are the fundamental building blocks of the universe. And their journey from simple beginnings to complex forms is entirely tied to the lives and deaths of stars. The very first stars, the universe's pioneers, were truly humble in their composition. They were almost entirely made of hydrogen and helium, the lightest and most abundant elements forged in the Big Bang. But these stars were also the universe's first alchemists. Deep within their cores, under unimaginable pressures and temperatures, they began the process of nucleosynthesis, the creation of new, heavier elements. It was a slow, steady cooking process, transforming hydrogen into helium, then helium into carbon and oxygen. These are the elements essential for life as we know it. Imagine the universe, in its infancy, patiently waiting for its stars to create the very ingredients it would need to build planets, oceans, and living beings. Then came the grand finales. For massive stars, the supernova explosion wasn't just a spectacular light show, it was the ultimate act of cosmic dispersal. The shockwave from the supernova was so powerful that it created even heavier elements, like gold, silver, and uranium, in that fleeting moment of intense energy. All these elements, from the relatively light carbon to the truly heavy metals, were then scattered far and wide across the interstellar medium. It's like a colossal cosmic seed dispersal, ensuring that the next generation of star systems would have a richer, more diverse palette of materials to work with. When you look at your hand, or at the trees outside, or even at the water in a glass, you are looking at matter that has undergone an extraordinary journey. The hydrogen in that water? It might have been around since the very beginning of the universe, but the oxygen? That was definitely forged in the heart of a star, possibly billions of years ago, and then scattered by a supernova. The carbon that makes up so much of your body, also a product of stellar fusion, the iron that carries oxygen in your blood, forged in the last moments of a dying massive star. This profound connection makes us truly stardust. It's not just a poetic notion, it's a scientific fact. Every atom in your body, every element heavier than hydrogen and helium, has passed through the fiery crucible of a star. You are literally made of recycled stellar material. This thought can be incredibly humbling, making us feel tiny in the face of such cosmic grandeur, but also incredibly significant, as we are part of this ongoing, magnificent narrative. We are a tiny, conscious expression of the universe's own recycling program. And this cycle isn't just a historical event, it's still happening all around us, constantly. New stars are forming right now in distant nebulae, drawing in the enriched gas and dust from previous stellar deaths. New planets are coalescing in the swirling disks around those young stars, built from the very same materials that formed our own Earth. The universe is a dynamic, ever-changing place, never stagnant, always transforming. It's an unending process of creation, destruction, and recreation, all powered by the life and death of stars. So, as we drift through this cosmic tapestry, remember that you are not just an observer. You are an integral part of this story, a product of stellar evolution, and a testament to the incredible, beautiful, and sometimes violent life cycle of stars. It's a journey that began billions of years ago and continues into the endless future. Let's keep journeying through this cosmic narrative, now shifting our focus from the broad strokes of stellar evolution to the subtle yet profound ways stars influence the spaces around them. We've talked a lot about the big dramatic events, births, fiery lives, explosive deaths. But stars, even in their quiet moments, are constantly interacting with their surroundings, gently shaping the universe in countless ways. Imagine our sun, a steady, middle-aged star. It's not just sitting there, it's constantly emitting a stream of charged particles called the solar wind. This is a gentle, invisible breeze of energy flowing outwards from the sun, reaching far beyond the planets. It's what causes the beautiful auroras, those dancing lights in the sky near Earth's poles, when these particles interact with our planet's magnetic field. You might feel a faint, tingling warmth on your face from the sun's rays, but imagine feeling that subtle, constant flow of particles washing over you in the emptiness of space. Every star in its own way creates a bubble of influence around itself. This is its heliosphere, or more generally, its astrosphere. It's a protective magnetic bubble that shields the inner parts of the star system from the harsher radiation and cosmic rays that zip through interstellar space. It's like each star carves out its own little sanctuary in the vastness, a safe haven where planets can form and life can potentially flourish. This constant interaction, this pushing back against the cosmic currents, is a quiet but crucial part of a star's existence. Beyond this direct influence, stars also act as gravitational anchors, holding together vast systems of planets, moons, asteroids, and comets. Our own solar system is a perfect example. All the planets, from tiny Mercury to giant Jupiter, are held in their graceful dance around the sun by its immense gravitational pull. Without that steady, unwavering grip, everything would simply fly off into the cold, dark reaches of space. Imagine reaching out to grasp the invisible fabric holding galaxies together. That fabric is gravity, and stars are the knots that hold it tight. And stars aren't just isolated islands. They are part of much larger structures, like immense galaxies. Our Sun, for example, is just one of hundreds of billions of stars in the Milky Way galaxy. Imagine our entire galaxy as a colossal, flat disk, slowly spinning in space, like a gigantic, luminous cosmic pinwheel. All the stars, gas, and dust are held together by the combined gravity of everything within the galaxy, including a mysterious, invisible substance called dark matter that we can't see but know is there because of its gravitational influence. Within a galaxy, stars aren't evenly distributed. They tend to cluster together in arms, creating beautiful spiral patterns, or in dense central bulges. They orbit the galactic center, just like planets orbit a star, but on an incredibly grander scale. Our Sun takes about 230 million years to complete one full orbit around the center of the Milky Way. Think about that. The dinosaurs were still roaming Earth the last time our solar system was in this part of the galaxy. It's a reminder of the truly immense timescales involved in cosmic processes. So, stars are not just isolated entities living out their lives. They are active participants in a vast, interconnected cosmic web. They emit whines that shape their surroundings. They provide the gravitational glue for their systems, and they move in grand celestial dances within galaxies. Each star, from the smallest red dwarf to the largest supergiant, contributes to the ongoing evolution and beauty of the universe, constantly interacting, constantly influencing, in a ceaseless flow of energy and matter. So, we've been picturing our Sun gracefully orbiting the center of the Milky Way galaxy, along with billions of its stellar siblings. It's a breathtaking thought, isn't it? This colossal spinning disk of stars, gas, and dust is our cosmic home, but our galaxy is just one of countless billions of galaxies scattered throughout the observable universe. Imagine that. Not just billions of stars, but billions of entire islands of stars, each one a universe unto itself. If you could zoom out even further, leaving the comforting spiral arms of our own galaxy behind, you'd start to see other galaxies. Some are spirals, just like ours, with graceful, sweeping arms. Others are smooth, round, and egg-shaped, looking like colossal, glowing cosmic pearls. These are elliptical galaxies. And then there are the irregular galaxies, chaotic and disorganized, often the result of galactic collisions or near misses. Each type tells a different story about its history and the forces that shaped it. You might even see faint hints of light from galaxies that are so far away. Their light has been traveling for billions of years to reach us, showing us what the universe looked like when it was much younger. And these galaxies aren't just sitting still in isolation. They are also moving, drawn towards each other by the immense pull of gravity. Galaxies aren't randomly spread out. They tend to cluster together, forming galaxy groups and even larger galaxy clusters. Our Milky Way, for instance, is part of a small group called the Local Group, which includes the Andromeda Galaxy, our nearest large spiral neighbor. Andromeda is actually heading straight for us. Don't worry though, it's a very, very slow cosmic collision, happening over billions of years. When galaxies collide, it's not usually stars smashing into stars, because the distances between stars are so vast. Instead, it's more like two huge clouds passing through each other, with gravity slowly reshaping both structures, sometimes even triggering bursts of new star formation. Imagine witnessing this galactic dance, these colossal islands of stars slowly drawing closer, their gravitational embraces gently reshaping their forms. It's a ballet of cosmic proportions, played out over timescales that are truly impossible for us to grasp in our daily lives. This movement, this constant interplay of gravitational forces, adds another layer to the continuous, ever-evolving story of the universe. It shows us that even on the largest scales, the cosmos is dynamic, always in motion, always changing. Beyond the clusters, the universe itself is expanding. It's not just that galaxies are moving through space, but that space itself is stretching, carrying the galaxies along with it, like spots on an inflating balloon. This expansion means that the farther away a galaxy is, the faster it appears to be moving away from us. It's a mind-bending concept, isn't it? The universe itself growing larger with every passing moment, carrying all these incredible structures, these vast collections of stars, further and further apart. And within this expanding universe, the cycle of stars continues. New stars are born in one galaxy, live their luminous lives, and then die, scattering their enriched elements back into the cosmic void. These elements then become part of the next generation of stars, perhaps in another galaxy that has just merged with their own. The universal story is one of continuous cosmic evolution, from the smallest atom to the grandest galaxy cluster, all interconnected by the fundamental forces and the incredible life cycle of stars. So, as we contemplate these vast scales, these immense structures, remember that every star, every galaxy, every cluster is part of the same grand, ongoing narrative. And you, gentle listener, are here, present in this moment, experiencing a tiny sliver of that unimaginable journey. Let's keep journeying through the cosmic expanse, now bringing our vast perspective back down to something a little closer to home, but no less marvelous. We've marveled at galaxies dancing and the universe expanding, a reminder that the cosmic story is always in motion. But within this grand, ever-unfolding narrative, there are countless smaller, intimate stories playing out. Consider, for a moment, the incredible diversity of objects that stars create or influence within their systems. We've talked about planets, of course, from scorching hot ones orbiting close to their suns to frozen, distant worlds far out in the darkness. But there's so much more. Imagine floating near a gas giant like Jupiter in our own solar system. It's a colossal swirl of colored clouds, immense beyond belief. But around it, dozens of moons orbit, each one a unique world in miniature. Some are icy, with potential subsurface oceans, like Europa. Others are volcanically active, like Io, constantly erupting with fiery plumes. And some, like Titan, are shrouded in thick atmospheres, with lakes of liquid methane on their surface. Each of these moons is a testament to the complex gravitational dance that takes place within a star system, and many of them hold secrets of their own, perhaps even harboring the conditions for life. Then there are the countless smaller inhabitants of a star system, the asteroids and comets. Asteroids are rocky remnants, often found in belts, like the one between Mars and Jupiter. They are bits of ancient material that never quite managed to form a planet. Comets, on the other hand, are icy wanderers, often originating from the very distant, frigid edges of a star system. As they approach the star, the ice turns to gas, creating those spectacular tails that we sometimes see streaking across the night sky. These humble space rocks and icy visitors are like cosmic time capsules, holding clues about the very earliest days of a star system, preserving the primordial dust and gas from which everything else formed. Now, as we drift through this cosmic neighborhood, you might notice something truly special about our own star system, the presence of life. We've discussed how stars forge the elements, and how planets form from those elements. But the leap from simple chemistry to complex, self-replicating life is perhaps the greatest mystery and miracle in the universe. Our Sun, a stable, long-lived main sequence star, has provided the steady warmth and light necessary for life to evolve and flourish on Earth for billions of years. It's truly a sweet spot, a perfect balance of conditions. Imagine standing on Earth, feeling the sun on your skin, watching the plants grow, breathing the oxygen that stars created. It's easy to take it for granted, but every breath, every heartbeat, every living thing around you is a direct result of that continuous cosmic cycle. The water in our oceans, the air in our atmosphere, the ground beneath our feet, and the very cells of our bodies all owe their existence to stars. And what about the search for life beyond Earth? As astronomers discover more and more exoplanets orbiting distant stars, the chances seem to increase that somewhere out there, other worlds might also harbor life. Perhaps not life exactly like ours, but life adapted to different conditions, different suns. It's a thrilling thought, a testament to the universe's boundless possibilities. The same processes that led to us are happening across the cosmos, setting the stage for perhaps countless other stories of life. So, as we bring our attention back to the intimate details of star systems, remember that each star is not just a light in the sky, it's the center of its own little universe, a complex and dynamic system where the ingredients of cosmic history are constantly interacting, creating, and evolving. And in some rare, precious instances, giving rise to the profound mystery and wonder of life itself. We've covered the grand story of a star, from its dusty beginnings to its dramatic end, and how it shapes the universe around it. But the journey of understanding isn't static, it's a continuous process of discovery. Astronomers, those dedicated stargazers and cosmic detectives, are always finding new pieces of the puzzle, always refining our picture of how stars work. It's a bit like peering through a cosmic keyhole, and with every new telescope and every new bit of data, that keyhole gets a little wider, showing us more of the breathtaking view beyond. Imagine you're an astronomer, sitting in a quiet observatory, thousands of miles from Randers, perhaps high on a mountaintop where the air is thin and the stars sparkle with incredible clarity. You're not just looking at points of light, you're collecting information. You're gathering the faint whispers of light that have traveled across unimaginable distances, each photon carrying a tiny bit of a star's story. By analyzing the colors of that light, how bright it is, and how it changes over time, scientists can deduce a star's temperature, its size, its age, and even what it's made of. It's like reading a cosmic autobiography written in light. One of the most exciting areas of discovery right now involves finding and studying more and more exoplanets. Every day, it seems, new planets are being discovered orbiting distant stars. We're finding planets that are vastly different from anything in our own solar system, hot Jupiters that orbit incredibly close to their stars, super-Earths that are bigger than our world but smaller than Neptune, and even planets that seem to float freely through space without any star at all. Each new discovery helps us understand just how diverse star systems can be and expands our ideas about where life might exist. It's like exploring a new continent every single day, uncovering new landscapes and possibilities. And then there are the ongoing mysteries, the things we don't quite understand yet. For example, what exactly happens right at the center of a black hole? Or how do the very first stars, those ancient population 3 stars made only of hydrogen and helium, actually form? We have theories, ideas, and mathematical models, but seeing them directly, really understanding the nuts and bolts, is still a challenge. These are the frontiers of our knowledge, the places where new discoveries are waiting to be made, beckoning scientists to push the boundaries of what we know. The universe is vast, and our understanding is still in its infancy, but that's what makes it so thrilling. Every new observation, every new calculation, every new idea adds another brushstroke to the grand masterpiece of cosmic understanding. It's a collective human endeavor, with scientists from all corners of the globe, from Denmark to distant observatories, working together, piecing together the incredible story of the universe. And in doing so, we're not just learning about stars, we're learning about ourselves, our origins, and our place in this magnificent, ever-unfolding cosmos. We've talked a lot about stars shining brightly, but what does that light actually mean? It's not just the visible light our eyes can see. The universe is actually buzzing with all sorts of different kinds of light, what scientists call the electromagnetic spectrum. Imagine a giant piano, and visible light is just one tiny section in the middle. Stars, and all cosmic objects, play notes across the entire keyboard, from low-frequency radio waves to incredibly high-frequency gamma rays. Each type of light tells us something different about a star. For instance, when a new star is forming, nestled deep within its dusty cloud, it might be hidden from our eyes in visible light. But if you could see in infrared light, you'd see it glowing brightly, like a warm ember, because infrared light can pierce through the dust. It's like having special glasses that let you see through a fog. And when a massive star explodes as a supernova, it sends out powerful bursts of X-rays and gamma rays, telling us about the most violent, energetic events in the cosmos. These are forms of light that carry so much energy, they'd pass right through you. Astronomers use special telescopes to capture these different kinds of light. Radio telescopes, which often look like giant satellite dishes, listen to the low-frequency whispers from distant galaxies and the remnants of supernovae. Infrared telescopes, sometimes placed high on mountains or even in space to avoid Earth's atmosphere, can peek into those dusty stellar nurseries. And X-ray and gamma-ray telescopes have to be placed in space, far above our protective atmosphere, to catch the universe's most energetic light. It's like having a whole orchestra of senses to perceive the cosmos, far beyond what our ordinary eyes can do. Think about what it would be like if you could suddenly perceive all these different forms of light. The night sky wouldn't just be twinkling points, it would be a vibrant, ever-changing symphony of invisible colors and energies. Distant gas clouds would glow with hidden warmth, and the violent aftermath of a star's death would flare with invisible, high-energy pulses. It adds a whole new dimension to our understanding of the universe, doesn't it? It's a reminder that there's so much more to space than meets the eye, a constant stream of information waiting to be decoded. This ability to see in different kinds of light is how we build up our incredibly detailed picture of stellar life cycles. By combining observations from all these different telescopes, scientists can piece together a more complete story. We can see the cold dust contracting, the warm protostar emerging, the bright, visible light of the mature star, and then the energetic X-rays from its dying supernova. It's like watching a movie of a star's life, from beginning to end, played out across the entire electromagnetic spectrum. This ongoing quest to capture and interpret cosmic light is how humanity continues to expand its knowledge of the vast, intricate universe we inhabit. Let's keep our cosmic journey flowing, now considering that many stars don't actually travel alone. We've explored the life of a single star, like our Sun, but it turns out that stars can be quite social. More than half of all the stars in the universe are actually part of binary star systems, meaning they have a partner star, and some even come in groups of 3, 4, or more. Imagine having a cosmic dance partner, orbiting each other, sometimes gracefully, sometimes in a frantic whirl, for billions of years. It adds another layer of complexity and beauty to the stellar story. Picture yourself floating near one of these binary systems. You wouldn't just see one sun in the sky, you'd see two, perhaps orbiting each other so closely that they appear to be touching, or maybe so far apart that they look like separate stars that happen to be near each other. The dance they perform is entirely governed by gravity. They pull on each other, constantly falling around a shared center point, a bit like two dancers holding hands and spinning around each other. The lives of stars in binary systems can be even more fascinating than single stars, because they influence each other. If one star is more massive, it will evolve faster, perhaps becoming a red giant while its smaller companion is still a healthy main sequence star. And sometimes, if they are close enough, the larger, expanding star can even begin to donate some of its outer material to its smaller partner. It's like a cosmic feast, where one star slowly siphoning off the outer layers of the other, forming a swirling stream of gas between them. This cosmic feeding can have dramatic consequences. Imagine gas slowly spiraling from a swollen red giant onto a compact white dwarf. As this gas piles up on the white dwarf's incredibly dense surface, it gets hotter and hotter. Eventually, enough hydrogen might build up on the white dwarf to trigger a sudden, runaway nuclear reaction on its surface, causing a brilliant, but much smaller, explosion than a supernova. We call this a nova. A nova isn't the death of the star, but more like a cosmic flare-up, a temporary brightening that can occur multiple times as the white dwarf continues to collect material from its companion. If you were watching, you'd see a faint star suddenly become hundreds or thousands of times brighter for a few days or weeks, then slowly fade back to its original dimness. And sometimes, in very rare and extreme cases, a white dwarf that is rapidly accreting material from its companion can reach a critical mass, a tipping point where its own internal pressure can no longer hold it up. When this happens, the entire white dwarf can detonate in a specific type of supernova called a Type Ia supernova. These are incredibly important events for astronomers because they all explode with almost the same brightness, making them like standard candles that can be used to measure immense distances across the universe. It's a very particular kind of stellar death, triggered not by the star running out of fuel from its own core, but by getting too much food from a neighbor. So, the social lives of stars are just as rich and varied as their solitary journeys. Whether they are gracefully orbiting, gently sharing their material, or dramatically flaring up, these multi-star systems add another layer of intricate cosmic ballet to the grand story of stellar evolution. They remind us that nothing in the universe truly exists in isolation. Everything is connected, constantly influencing and interacting in a magnificent, unending dance. We've seen how stars live, die, and even interact in pairs, sometimes sharing their very essence. But what happens to all that stuff they shed, that gas and dust from planetary nebulae and supernovae? It doesn't just vanish. It disperses into the seemingly empty stretches between stars, forming what astronomers call the interstellar medium. Imagine yourself floating in this incredibly diffuse cosmic fog. It's not empty at all, but incredibly sparse, like a whisper spread across an entire continent. This interstellar medium is mostly made up of the simplest elements, hydrogen and helium, leftovers from the very beginning of the universe. But crucially, it's also laced with tiny amounts of those heavier elements cooked up by previous generations of stars. Think of it as the universe's ongoing compost pile, enriching itself with every stellar death. These heavier elements are incredibly important. They are the cosmic spice that makes the universe more interesting, the building blocks for everything more complex than a simple gas cloud. Now, this interstellar medium isn't just a static, unchanging soup. It's dynamic, constantly being stirred and shaped by stellar events. When a massive star explodes as a supernova, it sends out a powerful shock wave that sweeps through the surrounding gas and dust, compressing it and heating it up. It's like a colossal broom sweeping through the cosmic dust, pushing it into denser clumps. These shock waves can sometimes even trigger new waves of star formation by creating new dense pockets in the gas clouds that then collapse under their own gravity. So, the death of one star can be the direct catalyst for the birth of many more. You might encounter different forms of this interstellar material as we drift. Sometimes, it's cold and dark, forming immense molecular clouds, where stars are silently brewing. Other times, it's lit up by nearby hot, young stars, glowing brightly as a nebula, like the famous Orion Nebula. These glowing nebulae are often vibrant with color, thanks to the different elements in the gas emitting light when excited by the star's radiation. Imagine drifting through a vast, shimmering cloud of reds, blues, and purples, each hue a sign of elements like hydrogen, oxygen, or sulfur glowing in the stellar light. It's a truly breathtaking, ethereal sight, a cosmic art gallery painted by starlight. These nebulae are not just pretty pictures, they are crucial windows into star formation. They show us where the action is happening right now, where new stellar nurseries are buzzing with activity. And as stars are born within them, they carve out cavities and shape the surrounding gas with their powerful winds and radiation, creating stunning pillars, intricate tendrils, and vast bubbles. It's an ongoing, creative dance between young stars and the gas from which they were born. So, the space between stars is far from empty. It's a vibrant, ever-changing environment, constantly being replenished and sculpted by the lives and deaths of stars. It's the grand arena, where the universe recycles itself, where the building blocks are reformed, redistributed, and made ready for the next cycle of creation. It's a testament to the universe's incredible ability to renew and transform itself in an unending, majestic cosmic ballet. Let's not just look at the cosmic canvas from afar anymore. Imagine now that we are actually inside one of those magnificent nebulae, one of those vibrant, glowing clouds of gas and dust. You're not just observing it, you're enveloped by it. The sense of scale is immediate and overwhelming. We're talking about distances so vast that light would take years, even centuries, to travel from one end of this cloud to the other. As you drift, you might feel a subtle, almost imperceptible warmth on your imagined skin. This isn't the scorching heat of a star, but a gentle, diffuse glow from distant stellar nurseries within the cloud. The colors around you are breathtaking, deep, velvety purples where hydrogen is glowing, brilliant electric blues from excited oxygen, and sometimes soft, ethereal reds where sulfur atoms are shedding their light. It's not just a flat painting. These colors shimmer and undulate, almost like a slow cosmic aurora borealis surrounding you in every direction. Now, listen. There's no sound in space as we know it, no vibrations to carry noise. But if you could perceive the subtle energy currents, the very fabric of this stellar birthplace, you might sense a deep, resonant hum. It's the gentle thrum of atoms bumping into each other, the quiet whisper of gravity slowly pulling gas together, the distant, faint crackle of newly forming stars in their hidden cocoons. It's the sound of creation, slow and steady, unfolding all around you. As you reach out your hand, there's nothing solid to grasp, only the incredibly diffuse, almost non-existent presence of gas and microscopic dust particles. Yet, within this seemingly empty space, something profound is happening. You might notice darker, denser knots of gas, like swirling shadows within the brighter parts of the nebula. These are the nurseries within the nursery, the places where gravity is winning its quiet battle. Here, hydrogen and helium, along with those precious heavy elements forged in older stars, are slowly, patiently drawing closer. Imagine reaching out to grasp one of these invisible, subtle currents of gas. You can't, of course, but you can feel its presence, the incredible sense of space stretching out, almost infinitely, yet filled with the promise of future suns. You are literally swimming in the raw material of stars and planets. Every atom around you has a story, a history stretching back to the Big Bang, or forged in the heart of a star that lived and died eons ago. And as you drift, you might suddenly catch sight of a tiny pinprick of brighter light deep within one of those dense knots. It's a baby star, a protostar, still wrapped in its dusty blanket, but beginning to shine, radiating heat and a faint glow. You are witnessing the very first spark of a new stellar life, a new sun slowly awakening, pushing back against the darkness. This isn't just a fact, it's a feeling, a profound sense of witnessing a universe that is constantly renewing itself, constantly giving birth to new wonders. This is the heart of creation, a place of quiet power and unimaginable beauty. You are there, floating in the cosmic quiet, the vibrant colors of the nebula swirling around you like an impossible dream. You've just caught that first glimpse of a protostar, a tiny glowing ember deep within a denser knot of gas. It's not a full-fledged star yet, remember, but it's rapidly getting there. Imagine feeling a slight increasing pull towards that central ember. It's the subtle, growing hand of gravity, ceaselessly at work, drawing more and more of the surrounding gas and dust inwards. As you watch, you might see the material around that protostar begin to flatten out. It's a slow, majestic swirl, like water draining from a colossal bathtub, but taking millions of years to do so. This is the accretion disk forming, that flat, spinning pancake of gas and dust. It's an incredibly important place, a cosmic construction yard where all the leftover building blocks are gathering. Imagine reaching out to touch it, feeling the incredibly tenuous, yet distinct, spiral of matter. It's beautiful in its silent, intricate motion, a testament to the elegant physics that shape the universe. And tucked within this disk are the very beginnings of future planets, slowly bumping and coalescing, hidden from view for now. Deep within the heart of that protostar, shielded by layers of collapsing gas, something truly monumental is brewing. All that material piling on, all that relentless squeezing from gravity, is making the core incredibly hot and dense. The pressure is mounting, the temperature soaring, reaching millions of degrees. It's a slow, patient build-up, a cosmic pressure cooker preparing for its grand revelation. You can almost feel the potential energy building, a silent tension in the heart of that forming star. And then, after perhaps 1,000,000 years or more for a star like our Sun, a sudden, yet gentle, shift occurs. The temperature and pressure at the very center of the protostar finally reach the critical point, the magic threshold. Suddenly, those tiny hydrogen atoms are moving so fast and are squeezed so tightly together that they can no longer avoid each other. They collide with such force that they fuse together, becoming a slightly heavier element, helium. When this fusion happens, an incredible burst of energy is released. It's not an explosion in the destructive sense, but a continuous, powerful, internal ignition. It's the moment the star truly turns on. This is the birth of a main sequence star. Imagine the instant that happens, feeling a profound surge of warmth, a deep, steady glow blossoming from the core. The outward push of this newly generated energy perfectly balances the inward squeeze of gravity. It's like a cosmic dancer suddenly finding their perfect, stable equilibrium, arms outstretched, holding their pose for an incredibly long time. For the first time, you could truly see this newborn star with your own eyes, brilliant and clear, as its powerful winds and radiant light push away the last wisps of its dusty birth cocoon. It stands revealed, a vibrant, steady beacon, ready to shine for billions of years. Our own sun is in this exact phase right now, reliably fusing hydrogen into helium, giving life to our world. Feel that steady, comforting warmth radiating from it, a cosmic hearth burning for eons. It's a profound moment, isn't it? The universe creating its own light, its own enduring warmth. So, here it is, our star, a beautiful main sequence star, much like our own sun, shining steadily in the vast darkness. This is the longest and most stable phase of a star's life, a period of remarkable cosmic equilibrium. Imagine yourself drifting alongside it for what feels like an eternity. For a star of this size, this phase will last for billions of years. Think about that. Billions of years of constant, unwavering light and warmth, just like the reliable sun you might see rising over Randers this morning, a Saturday in June. It's truly a testament to the universe's incredible patience. During this immense stretch of time, the star is in a perfect, delicate balance. Deep in its core, that tireless process of nuclear fusion is happening, constantly mashing hydrogen atoms together to create helium, releasing that incredible surge of energy. This energy pushes outwards, gently but powerfully. And perfectly counteracting that outward push is the relentless inward squeeze of gravity, trying to collapse the star. It's a cosmic arm wrestling match where neither side ever gains the upper hand, and that perfect stalemate is what makes a star so remarkably stable for so long. You might feel the steady, reassuring warmth emanating from the star's surface. This energy, born in the core, slowly, patiently works its way through the star's layers before radiating out into space as light and heat. It's a continuous flow, a river of cosmic power that can warm distant planets and even give rise to life. Can you picture that incredible output, a ceaseless fountain of energy from such a seemingly simple process? It's the universe's most efficient and enduring power plant, quietly running for eons. Our own sun, a comforting yellow star, has been in this phase for about 4.5 billion years, and it's got roughly another 4.5 billion years to go. It's been providing the perfect conditions for life to flourish on Earth for a very long time, and it will continue to do so for billions more. It's a reliable friend in the cosmic neighborhood, always there, always shining. But nothing lasts forever, not even a star's long, stable life. Eventually, slowly, subtly, the star will begin to run out of its main fuel, the hydrogen in its core. It's like a cosmic engine that's been running for an incredibly long time, and now its primary fuel tank is starting to get low. This isn't a sudden event, but a very gradual shift, almost imperceptible at first. As the hydrogen in the core dwindles, the delicate balance begins to tilt. With less outward pressure from fusion, gravity starts to gain the upper hand. The star's core, now mostly filled with helium ash, begins to contract. It shrinks and gets even denser and hotter. This contraction, surprisingly, generates a lot of heat, warming the layers of hydrogen that are just outside the core. It's like the main furnace is running low, but the heat from its embers ignites a smaller, secondary fire around it. This newly ignited shell of hydrogen fusion starts producing a huge amount of energy, even more fiercely than the core did before. This extra energy pushes the star's outer layers outwards, causing the star to expand dramatically. It swells up, growing to an unimaginable size, far, far larger than it ever was during its main sequence life. As it expands, its surface cools down, which makes it glow with a deep, magnificent red color. This is when our star transforms into a red giant. Imagine watching our familiar yellow sun slowly, majestically swell up, growing so large that its outer edge would swallow Mercury, then Venus, and possibly even engulf Earth. It would be an immense, fiery red orb filling the sky, a truly breathtaking sight, signifying a majestic old age. This is the star's grand transformation, its slow, powerful exhale as it enters the next, very different, chapter of its cosmic life. You are still drifting there, witnessing a sight of cosmic proportions. Our familiar yellow sun, or a star much like it, has swelled up to an unbelievable size, a truly enormous, fiery red orb. Its outer layers are now incredibly diffuse and stretched thin, so far from the core that the light and warmth you feel, while immense, is spread out over a vast area, giving it that cooler, reddish glow. Imagine if you could scoop up a handful of its outer atmosphere. It would be far less dense than the air you're breathing right now in Randers. It's a grand, majestic phase, a testament to the sheer power of an aging star. Inside this colossal red giant, even as the outer layers expand, the original core continues its relentless squeeze. It's like a tiny, super-dense kernel at the heart of this colossal puffball. This core, now primarily made of helium, gets hotter and hotter, denser and denser, as gravity just keeps on compressing it. The pressure within it reaches utterly staggering levels, far beyond anything we can imagine on Earth. And then, just like before, when hydrogen first ignited, a new kind of fusion begins. The temperature and pressure in the helium core finally become so extreme that the helium atoms themselves start to fuse. They combine to form heavier elements, primarily carbon and oxygen. For stars like our Sun, this ignition of helium can happen quite suddenly in what's sometimes called a helium flash, a quick, powerful burst of energy that then settles into a new, steady burn. It's like a cosmic hiccup, followed by a deeper, more profound hum. With this new energy source, the star finds a brief new equilibrium. It's still a giant, of course, but it has a renewed lease on life, fueled by helium burning in its core and still a little bit of hydrogen burning in a shell around that core. However, this helium fuel burns much faster than hydrogen did. Think of it like burning a thick, heavy log versus burning a pile of kindling. The log burns hotter and quicker. So, this phase, while still lasting millions of years, is considerably shorter than its main sequence life. As the helium in the core eventually runs out, the star faces another energy crisis. The core, now mostly a dense ball of carbon and oxygen, begins to contract again, squeezing even tighter. And just like before, this causes the layers surrounding it to heat up. Now, a new shell of helium burning ignites, outside the carbon-oxygen core, along with the hydrogen-burning shell further out. This creates a powerful surge of energy that pushes the outer layers of the star outwards even further than before. Our star becomes an even grander, puffier red giant, sometimes called an asymptotic giant branch star. It's its final, majestic stretch, its ultimate expansion. During this magnificent, puffed-up stage, the star's outer layers become incredibly loosely bound by gravity. They are so far from the core, and the star is generating such immense energy that these outer layers simply begin to drift away into space. It's not a violent explosion, but a gentle, steady shedding, a slow, beautiful exhalation. Imagine yourself gently pushing away a cloud of cosmic dust with your hand. That's the scale of this gradual release. The star is slowly, serenely letting go of its outer skin, sending its material out into the universe. As these beautiful outer layers expand and drift away, they are illuminated by the intensely hot, exposed core of the star that's left behind. This creates what we call a planetary nebula. And remember, it has nothing to do with planets. Despite the name, these are stunning, often colorful shells of gas, intricately shaped and glowing with vibrant hues of red, blue, and green. Each planetary nebula is unique, a cosmic masterpiece, a vibrant final farewell from a star that has lived a long and luminous life. Imagine floating right next to one, seeing the ethereal tendrils of glowing gas swirl like cosmic smoke, a final, radiant burst of stellar art. We've just been bathed in the ethereal glow of a planetary nebula, that breathtaking cosmic artwork created by the gentle shedding of a star's outer layers. It's like the universe's ultimate fireworks display, but in slow motion, played out over tens of thousands of years. As you drift, you can see these beautiful, shimmering clouds expanding outwards, slowly fading, becoming more diffuse, eventually dispersing and blending back into the vast, thin gas of interstellar space. It's a peaceful dissolution, a return to the cosmic well from which new things will one day emerge. But what about the star itself, the heart of that beautiful nebula? After all that shedding, what's left behind is its exposed core. Imagine taking something as massive as our Sun, something that once swelled up larger than Earth's orbit, and squeezing almost all of its remaining material into a sphere roughly the size of Earth. That's how incredibly dense this remnant is. This tiny, super compact, intensely hot core is what we call a white dwarf. Picture this. A teaspoon of white dwarf material would weigh not just pounds, but tons, perhaps even more than an entire elephant. It's truly mind-boggling, isn't it? The atoms inside have been crushed so tightly that their electrons are packed together as closely as physics allows, creating an incredible resistance that finally stops the collapse. It's still incredibly hot when it first forms, glowing with a brilliant white light from its leftover heat. That's where the white in white dwarf comes from. It's no longer fusing anything in its core. The nuclear fires have gone out. This is a stellar cinder, slowly cooling down. Think of it like a dying ember from a campfire that you might gather around on a cool evening in Randers. It glows brightly at first, then fades to a warm red, and eventually it turns cold and black. A white dwarf goes through a similar, but incredibly slow, process. It simply radiates away its stored heat into the cold vacuum of space. This cooling process takes an extraordinarily long time, far, far longer than the current age of the universe itself. We're talking about trillions of years. Over these immense, unimaginable timescales, the white dwarf will continue to cool, getting dimmer and dimmer. Its brilliant white glow will slowly fade to yellow, then orange, then a faint red. Eventually, after eons beyond our comprehension, it will become completely cold and dark, a black dwarf. This black dwarf would be an inert, solid lump of carbon and oxygen, drifting silently through the cosmic void, a truly dark star. It would emit no light or heat of its own, making it almost impossible to detect, a cosmic ghost, a memory of a star that once shone brightly. It's important to remember that because the universe isn't old enough, no white dwarfs have had enough time to cool down completely to become black dwarfs. So, for now, they exist only in our theoretical understanding of how stars like our Sun eventually meet their ultimate quiet end. This gentle fading, this slow descent into darkness after billions of years of shining, is the destiny for stars similar to our Sun, and for all stars up to about 8 times the Sun's mass. They live long, stable lives, have a magnificent final expansion as a red giant, shed their outer beauty as a planetary nebula, and then slowly cool down into these incredibly dense, dim remnants. It's a peaceful, quiet ending, a profound cycle of light to dark, matter to energy, and back again, endlessly recycling the building blocks for new stars, new planets, and perhaps even new life. Somewhere far, far in the future, we've seen the serene, gentle fading of stars like our Sun into white dwarfs and, eventually, theoretical black dwarfs. But now, let's turn our attention to the true giants of the cosmos. Imagine stars that are 8 times, 10 times, even 100 times more massive than our Sun. These colossal stars live incredibly fast and die with spectacular force. Their lives are much, much shorter, often lasting only a few million years compared to the billions of years for a star like our Sun. It's like they're burning through their cosmic fuel at an incredibly furious pace, living life in the cosmic fast lane, all energy and brilliant light. Just like smaller stars, these massive stars spend most of their lives on the main sequence, fusing hydrogen into helium in their cores. But because they are so much more massive, their cores are far hotter and denser. This means fusion happens at an exponentially higher rate. They are truly the brightest beacons in the night sky, often shining with a brilliant blue or white light. You can almost feel the intense energy pouring off them, a radiant heat that would simply vaporize anything that got too close. When these massive stars start to run out of hydrogen in their core, they also expand, but not just into red giants. They become supergiants. We're talking about stars so immense that if one replaced our Sun right now, its outer layers could extend past the orbit of Jupiter, or even all the way out to Saturn. Imagine our entire solar system swallowed whole by a single colossal star. It's a breathtaking and humbling thought. These supergiants are often reddish, like their smaller red giant cousins, but on a scale that is almost impossible to comprehend. Picture that immense, glowing orb, bigger than any planet we know, filling your entire field of view in the cosmic dark. Now, here's where the difference truly begins for these stellar heavyweights. For these massive stars, when the hydrogen in the core is used up, and even when helium starts fusing into carbon and oxygen, the story doesn't stop there. Their immense gravity keeps squeezing the core, making it hotter and hotter, denser and denser. This intense pressure allows these stars to fuse heavier and heavier elements. They become like cosmic onion layers, with different fusion reactions happening in shells around the core. First, helium fuses into carbon and oxygen. Then, carbon fuses into neon and magnesium. Next, neon transforms into oxygen and silicon. And finally, silicon fuses into iron. This process continues, building up heavier elements in the core, layer by layer, until the very center is packed solid with iron. And this is where the star hits a cosmic brick wall. Iron is unique among the elements in this stellar fusion chain. When iron atoms are fused together, they don't release energy, they actually absorb it. It's like trying to build a fire with wood that just soaks up all the heat instead of giving it off. So, once the core of a massive star is filled with iron, There's no more energy being generated to push outwards and counteract the crushing, relentless force of gravity. At this critical point, the delicate cosmic balancing act that kept the star stable for millions of years suddenly, catastrophically, fails. The core, no longer supported by outward pressure from fusion, collapses in on itself with incredible, terrifying speed. We're talking about something the size of Earth collapsing down to the size of a city, all in a fraction of a second, mere milliseconds. This is an implosion of unimaginable power. As the core collapses inwards, it slams into its own incredibly dense center and then, in a cosmic rebound, sends a powerful shockwave hurtling outwards through the star's remaining layers. This rebound, this outward-moving shockwave, is what triggers one of the most spectacular and violent events in the universe, a supernova. It's an explosion so incredibly powerful that for a brief period of time, a single supernova can outshine an entire galaxy, shining brighter than hundreds of billions of stars combined. Imagine that. One star, in its dying gasp, becomes a cosmic beacon of unparalleled brilliance. If you were close enough, you wouldn't just see it, you'd feel it, a colossal wave of energy washing over you, a profound tremor in the very fabric of space. This explosion blasts most of the star's material, including all those precious heavy elements forged during its life, out into space at incredible, breathtaking speeds. These elements, like the oxygen for our air, the carbon for our bodies, the iron for our blood, and even the gold and silver we prize, were all forged in the heart of these dying stars and scattered by their magnificent, violent ends. We are, quite literally, made of stardust. We've just witnessed the most explosive and powerful event in the universe, a supernova. Imagine that blinding flash fading into an expanding, turbulent cloud of glowing gas, slowly dispersing into the vastness. It's a cosmic canvas being repainted with the fundamental building blocks of everything that will ever be, and what's left behind at the heart of that incredible violence. For some stars, it's a super-dense neutron star, a tiny, impossibly heavy city-sized beacon, spinning furiously, perhaps sending out rhythmic pulses like a distant cosmic lighthouse. For others, the most massive ones, it's the ultimate enigma, a black hole, a region where gravity is so profound that even light cannot escape, a silent, mysterious well in the fabric of space and time. These incredible remnants, whether glowing neutron stars or invisible black holes, are the ultimate destinations for stars at the end of their most dramatic lives. But their story, like all stellar stories, isn't truly an end. It's a continuation. All that material blasted out by the supernova, all those precious heavier elements that were painstakingly cooked up inside the star's core for millions of years, they don't just disappear. They are flung far and wide across the galaxy, enriching the interstellar medium. Imagine those tiny, ancient atoms, perhaps a bit of carbon, a speck of iron, or a glimmer of gold, now drifting freely through the cold, vast quiet between stars. They are the cosmic seeds, the legacy of a star that lived and died in a blaze of glory. They mingle with the hydrogen and helium that has been around since the very beginning of the universe, slowly, patiently mixing. Over immense spans of time, these enriched clouds of gas and dust will feel the subtle, relentless pull of gravity once more. They will slowly condense, fragment, and collapse, forming new molecular clouds, new stellar nurseries. And within these new nurseries, new protostars will begin to form, drawing in material that is now richer, more complex, infused with the stellar dust of previous generations. These next-generation stars will be born from the ashes of their ancestors, carrying within them the very elements that were forged in the hearts of old, dying suns. It's a profound thought, isn't it? The universe truly does recycle. Death isn't an end, but a transformation, a necessary step in the unending cycle of cosmic creation. And from these enriched clouds, not only new stars, but new planets will also form in swirling protoplanetary disks. Planets made of rock and metal, because now, thanks to those supernovae, those heavier elements are abundant. Planets like our own Earth, with liquid water, diverse minerals, and an atmosphere. Planets where, in rare, precious instances, the conditions might just be right for the ultimate miracle to unfold, the emergence of life. Think about that for a moment as you sit wherever you are. perhaps a quiet early morning in Randers. Every atom in your body, every element heavier than hydrogen and helium, has passed through the fiery crucible of a star. You are literally made of stardust. The carbon in your cells, the oxygen you breathe, the iron in your blood, all of it was forged in the hearts of stars and scattered by their magnificent deaths billions of years ago. We are, quite simply, the universe becoming aware of itself, made from the very elements that stars created and dispersed. It's a humbling, yet deeply connecting realization. We are not separate from the cosmos. We are an intimate, intricate part of it,